So first of all, I start by saying it's a kind of a moonshot. And actually, our name is Mercurius, which is a planet, so we are...
Use this if you want, or you can click. Tac.
Okay. Okay. As you want. So, basically, our vision is to transform sports betting into a new financial asset. So, it may sound weird, but as you know, prediction markets like stock market is said to be efficient, non-efficient. So there are some, there is some room left in the betting market, which behaves quite similarly to the stock market, let's say. And we found that there are many inefficiencies that we want to exploit to build what we believe will be a new financial instrument. Let's start by saying what may sound obvious, which is the house always wins. That's what we are told all the time when we are headed to a casino, for example. Actually, it's not completely true, because there are some activities like sports betting which are based on skill, like poker. It's not a matter of luck, it's a matter of skill. So, actually there is a 5% of bettor that wins systematically. So it is not luck, it is again skill. But, and this data is confirmed by the Gambling Commission in the United Kingdom. Can you hear me? No? Oh, probably just... Oh yeah, it's battery. We search for the other. Okay. So, okay. No. Sasa Pro. Okay. So basically, just like professional traders make very stressful decisions, make a lot of analysis, they spend a lot of time analyzing tons of data. Professional bettors do the same, and this is really time consuming, it's a full-time job. So really a few amount of people can afford to do that, both for the skills that are required and for the time a person has to allocate for this kind of activity. Another hidden feature, hidden problem, is that sports data is extremely expensive. So there isn't yet a full community of sports analytics or applied researchers that focus on sports, and in particular with a possible application in the betting market, which is usually not so well seen. So the solution is a robo-advisory service that makes all this work for you, which is all completely automated, and that is based on risk management and machine learning algorithms that runs football data at the moment. So basically, we use statistical models to define what are the event probabilities, for example, of a team winning at home or losing, and we define what are the right price to, in the betting jargon, the odds. What are the good odds to buy, let's say, in order to have a profit over the long term. Over the long term means after hundreds of bets, not just, as you may know, it's not a matter of winning one bet, but to have a statistical edge over the long run. So after 1,000 operation, I expect to have some margin. And so this is the solution we are proposing. So since we are basing this activity on two aspects, which are quite different, we have on one side the analysis of the sports data. On the other one, we have the risk management part, which basically selects how much to allocate in a single operation. So we divided and decided to call them the heart and the head of our service. And since we like agile and fast, at the agile methodologies, we decided to build a so-called minimum viable product, which is online. You can browse on the internet and find Mercurius.io. And basically now you can set up your investment. You say the amount of money you want to invest, let's say over 1 year. You choose a strategy. In this case, we only implemented one, which is anti-aggressive one, the one we call contrarian. Then you will have, every day you will find in your market page a list of adjusted operations with the relative, with the associated bookmaker, which is the party accepting the bet, the minimum odd, which is computed by our system, and the detail of the match on which you will bet. And then there is our pre-port stage, which is what we call the dashboard. So basically a graph where you can overview your performance over time and see what operation was successful and which one was not. And then we get into the details probably you are interested in. So how can we mathematically model the beautiful game, football, for example? Let's start with data. What are the main data we should consider when modeling football? So, for example, of course, the most important one is goal. So, if a team that scores many goals is stronger than a team that scores fewer. And a goal is a consequence of a shot. So basically we are focusing on these data. Actually, we may also focus just on goals scored. Why? Because you see, they follow a well-known pattern, actually. They are kind of distributed as a Boston variable. So here, for example, we see the goals scored in a game for a 12-year period in the English Premier League. And we see that the fit is quite neat. There is another option. We know that at home, teams tend to score more often than when playing away. For example, in the English Premier League, where this effect is quite remarkable, there is a 33% frequency, which is like a really nice factor to take into account. So basically, our model, which is implemented now, is to assign, let's say, a rating for each team, depending on some factors, for example, how many goals they scored against a stronger team or a weaker team, or so there are some hidden factors which are not here, which are in the attack home or defense away, let's say, variable. But the important thing is that there is also the global tendency to score, which is specific for each tournament, and the home effect, which is specific for each team, or for specific tournament. There is a kind of interaction here. The results is that the results are not so bad. We see that, especially for 3 or more goals, the distribution is quite follows quite the theoretical one. We have some problems, but not so remarkable. When estimating 0 goals game, for example, we tend to overestimate them. Whereas in the 1 or 2, there is an underestimation of the frequency. So, and this is the let's say, how often the model predicts the actual outcome. So here we see that for the away team, performances are quite good, but there is a big, let's say, mistake, which is draws. Our model struggles to capture what causes a draw. And this is a kind of open question in the field. Like, it's quite hard to understand in which situations team draw, because it's a kind of strange results. Nobody wins, nobody loses. And So let's draw some conclusions. This model has a fairly good accuracy. It's simple. It's not CPU intensive. It's a good and well accepted benchmark. On the other side, we have that we considerably underestimate draws. There is also an underestimation of what we call low-scoring games. Games where teams are like similar to each other, and they tend to give life to a really tight match. And of course, there are some simplistic assumptions. For example, in this model, we assume the goal scored by a team is independent, but is independent of the goals the other team scores. So, of course, we have some improvements that are possible. For example, we can see that in the low-scoring games, where the differences are in goals are small, we may apply some adjustment to take into account this factor. And let's say that behind the Poisson distribution, there is the assumption that the process is, let's say, homogeneous over time. In reality, it's not true, because we all know that there are a lot of, and we also see, there are a lot of goals in the last minute, or in the recovery time, or just before half time. So we may try to plug this information in the model. But then for future research, we may take into account also the shooting aspect. So let's see that this was the old model, and let's introduce a new advanced metric, which is the expected goal. So basically, we want to take into account the shot number during a match, the shot position. Of course, a shot that was taken far away is harder to convert in a goal, and also shot details. This is how, of course, we represent the pitch. Let's say we center our coordinate system at the center of the goal, and we may try to plot the corresponding distribution, of like probability of scoring versus the distance of the shot. And we see some like fairly intuitive insights. Of course, it is a kind of a power law. So the further we go, the less, the smaller is the probability. Actually, we also see a peak in the 11 meters, which corresponds to a penalty kick. So it's not so strange. Things get a bit bit more difficult when approaching the goal. Like there is a kind of exponential increase in probability that does not fit well with the power law. So it also is a sign that there must be some other factor inside, and it usually is the body part we use to take the shot. So if it was a header or a shoot, when we are in the 15 meters area, it changes a lot. We may see this problem as a classification problem, because a shot is either convert to a goal or it doesn't. So a common approach is to define it as a classification problem. And this is the kind of data we plug into the system. Of course, we need the number of shoots, the position, and the details for each game. So actually, we cannot pre-compute these statistics before the game is played. So it's a kind of descriptive metric we can use to improve our pre-match models. And for example, in this case, and this is relative also for the English Premier League, we see that there is a nice fit between a nice correlation between the served goals and the expected one. So, for example, here we compare the two different models. The SVM was trained using also the detail of the distance, whereas the naive one just took into account the number of shots in a game. So here we see that, of course, plugging also the distant information improved the model. So what we may conclude that in soccer, and not only in soccer probably, the best defensive strategy is to attack. And there are also some data about our user base, because we decided to go online 1 year ago, offering our users this betting strategy, which is based on the first model. And actually, there was a lot of interest. So people started engaging with the platform. They quite liked the idea of robot advisors that crunches number about football. And this also shows that people, once they start betting with our strategy, or just paper trading, so just following on paper our suggestions, they kind of get the point of betting every weekend on value bets and on profitable, on the long-term operations. So what we see is that users, of course, don't select every operation. They tend to think that they are smarter than a machine, so they do not quite follow all of our advices. So what we see is that after a given threshold, so let's say 150 bets, almost everyone is profiting, which is quite unusual because the 95% of people loses gambling money on sports. And this is the team. We are a broad team which involves betting and regulation aspects, software expertise, and of course the data part, which is extremely important. On the other side, we also have to say that, as I said, sports data is quite expensive, so we are now accepting investments in order to let's say, to pay for this kind of asset, and we are also considering changing a little bit our business model. It will be a kind of hedge fund. You will deposit money in some way, and after 1 year, you will collect the performance you were able to achieve in the meantime. And it will be, let's say, a betting vault. You won't need to create your betting account, to send the information to the bookmaker. So we are in fundraising mode in order to implement also this kind of automated betting investment fund.
So since then we run a little bit out of time, we will only have time for one question. Okay.
How do you make money?
I was told this speech was not about business modeling, so I removed the slide. It will be revenue sharing.
Okay, thank you very much.